All right. Okay, so it's my great pleasure to introduce Jackie Chung. So he's an associate professor at McGill University in the School of Computer Science, and he also co-directs the Reasoning and Learning Lab. And he's also a Canada CFAR AI chair at the Mila Quebec AI Institute. So I've had the pleasure to know Jackie over the years. He's really a world leader when it comes to natural language processing, very well known throughout Canada and the NLP community. So his research focuses on natural language generation tasks that includes automatic summarization, as well as integrating diverse sources of knowledge into NLP systems for pragmatic and common sense reasoning. Now, he's motivated in particular by how the structure of the world can be reflected in the structure of language processing systems. And he's also served as a consulting researcher for Microsoft Research in Montreal. So without any further ado, I'll let Jackie go ahead. And the title of his talk is Keeping Track of Entities Over Time, Minds, and Knowledge Sources.
Thank you very much. So thank you so much, Pascal, for inviting me. It's a really great pleasure. Yeah, I've known Pascal throughout the years in many different ways, so it's really wonderful to be here now to speak with you guys. And I'm sorry I couldn't visit in person, but hopefully that will change soon in the near future. Yeah, so my talk is about NLP, and I think how I see what are the developments that are exciting currently in NLP and going forward, especially on the side of evaluation and what people should be working on in the first place. So let me start with that kind of story. So as I'm sure you know, in NLP and in machine learning, over the last few years, one of the biggest stories in NLP has been these pre-trained language models like BERT and all of the varieties that have come out. And the most recent one I've seen is called Megatron from NVIDIA. And I think it's just called Megatron because it's a cool name and it's really big, and that's the justification. But anyway, so there are all of these large pre-trained language models. And then in terms of some of the benchmark evaluation suites that people in NLP have proposed and applied these types of models on, they perform really, really well. So for example, GLUE and SuperGLUE are two of these types of evaluation benchmark suites. And you can look down the list to see the human level performance compares to the performance of the top ranking systems. And every time I give this talk, I have to revise the slide because every time the human level performance is lower and lower in terms of ranking. So for example, on the original GLUE benchmark, the human level performance is now ranked number 22. And even on SuperGLUE, which is like a later version of this, it's now ranked at number 6, whereas all of the top ranking models are based on this idea of taking a large amount of raw text, doing some kind of pre-training on it with a transformer-based model, and then fine-tuning on these various tasks and evaluating. So from that perspective, NLP has been doing really great by leveraging these deep learning techniques and pre-training. And it's in terms of these applications and these evaluation settings, it's all the performance numbers are really, really well and are better than human. But it's not just the application perspective. There's another perspective here, which is in terms of more of a cognitive science and neuroscience flavor. So this is a study that came out last year from Shrimp et al. And from MIT. And what they found was that these large pre-trained language models are also very good at predicting internal neural representations from people and also to predict human behaviors. So how they did this was that they trained these large language models and then they fine-tuned them to predict, say, fMRI readings that they got from people who are reading. And they found that there was a very high correlation that can be measured and explained by these large language models. And similarly, they did this with looking at human behaviors by getting people to read text and looking at their reading times. So they can do eye tracking and do other studies to measure the amount of time it takes for humans to read the next word. And they show, again, that the same kind of models can have very high predictive power, essentially predicting all of the explainable variants in their studies according to these measures. And so that's evidence that these large language models, they are capturing something that is not just in terms of the applications either. So in terms of these neuroscience studies, there's also great progress there. And notably that these large language models are the type of models that does the best at these types of tasks. They tried other things, like they tried fine tuning on like natural language inference tasks and other kinds of tasks that are popular in NLP, and they don't do nearly as good of a job at predicting these scores, having correlations with these scores. So then one question that you might ask is that maybe this is it for NLP. So we have transformer models, and this is the be all and end all of everything in NLP. And that's what we're going to be working on. And the best way to then spend our time is to just keep scaling up these models, making them bigger and bigger, and training on more and more text. And so, so this is evil Bert that's taking over NLP, perhaps, and that's all everyone should be working on. So the way I'm setting this up, you'll probably be able to predict that I don't think that this is all there is to NLP, and there's still a lot of other interesting tasks and problems to work on. And some evidence towards that is that there are another set of results that show something a little bit less rosy in terms of the behaviors of these systems. So some of these are position papers and theoretical criticisms, and they're really interesting to read. So for example, Bender and Kohler in 2020 came up with a provocative position paper about whether we're climbing towards the right hill in NLU, in natural language understanding, because they think that there's something fundamentally wrong with only looking at word co-occurrence, which is about the form of language rather than the contents of language and what they refer to. And there are other reasons that some researchers think that AI is maybe harder than we think. This is another position paper by Margaret Mitchell. And experimentally, you can also show that the pre-trained models that are possibly then fine-tuned exhibit some unexpected behaviors under stress tests. For example, in natural language inference, so the task of figuring out whether one sentence entails another sentence, there's been a data set called Hans that is specifically targeting whether current models are influenced by word overlap. For example, you can have as one sentence like the doctor believed the lawyer saw the officer. And you can ask, does this entail that the doctor believed the lawyer? Well, if you ask people this, they would say no, because the doctor believed the entire clause about something like happened, whereas the sentence that you're testing against is about the doctor believing the lawyer overall. It turns out that they show that with this type of data and this type of data set, the currently popular systems don't do well at it at all. The performance drops substantially. And so it seems to suggest that the current models are influenced by the amount of word overlap or n-gram overlap between the premise and the hypothesis. And in some other work that we've done in my group, we've also shown similar things in other kinds of tasks related to common sense reasoning. And so there are issues with the consistency of these models that suggest that maybe they're overfitting to the task, or they're learning something that is not like the reflecting decisions based on a proper understanding of the world. Here's an example from something called the Winograd Schema Challenge. You can have something like Emma did not pass the ball to Janie, although she saw that she was open. And in terms of the task, it's to figure out who she refers to. Is it referring to Emma or to Janie? And so this requires some kind of imagination of a scenario with like basketball or something. And so if you see that somebody else is open, then it might mean that you have the ball, which means that you would be able to pass the ball, right? So that's the kind of basis of understanding that humans might use in order to decide that she refers to Emma. So one study that we did was that we perturbed the question and we swapped the order of the names. So in this particular evaluation set, the names are just there. They're just like there to point to the entities. So there's no other information attached to the names. So what we found was that if we swap the order of the names, the models that we tested at that time, which were based on what was popular then in terms of the language models then to solve this Winograd Schema Challenge, they were heavily influenced by this. And the performance of the systems dropped from something substantially better than random to essentially close to random again, which again shows that the models were not making these ambiguity resolution decisions based on an understanding of the world the way that humans would be. And there are a variety of other studies that you can do with this. We're only like one of the groups that have been working on this style of evaluations and probes. Here's another one, which I think is easy to understand and interesting. If you ask BERT to predict what it knows about the world in terms of like taxonomic relations, it's also not consistent between singular nouns versus plural nouns. So if you ask it like Robin is a mask, and you get a bird to try to predict between a set of high-level categories, like birds versus mammals versus vehicles or whatever, then it does really, really well in the singular form. But then if you then ask it in the plural, like robins are masked, then it's not consistent anymore, and it predicts another high-level category, robins are flowers. So this is beginning to get us to see that perhaps large language models, as they currently are by themselves not able to systematically solve a bunch of these tasks that seem to require some kind of a common sense reasoning or understanding about how the world works. And another paper last year has done this even more systematically. This one is from AI2. So what they did was that they looked at the training dynamics of large language models over time, throughout the process of pre-training. And then they did this on a large number of different evaluations and data sets to try to get a more systematic understanding of what the models are good at right now and what kinds of tasks that they're not so good at. So in this particular chart, on one axis, on the vertical axis, you have the different types of evaluation suites. So some of them they call linguistic, and they involve extracting structure from the text as classically defined in the NLP pipeline. Like, for example, doing part of speech tagging or doing syntactic chunking, which is like finding like where all the noun phrases are in a sentence, or name entity recognition, and so on and so forth. And then another set of tasks have to do with factual knowledge recall or common sense reasoning, similar to some of the examples I showed you in the previous slides. And then lastly, they also have another set of evaluations involving what they call reasoning. So these would be the things like, can you reason from like a universal statement to an existential statement and show that there's an entailment relationship there, that kind of thing. Or doing like multi-hop question answering, where you have to use like multiple facts and knowledge and like string them together to make a further inference. And then this plot shows the performance of a language model that's being pre-trained over time and then tested on these different tasks with various baselines and top lines and so forth. And the interesting thing that they found was that in terms of all of the linguistic extraction tasks and the linguistic recognition tasks of like subject-verb agreement or so forth, these models do really, really well. So they acquire this competency really quickly and stably and like almost all the time, and it stays there and it converges. What's harder, it seems, is like all of these factual and common sense evaluations where the performance is more varied, it's slow, and it seems to be domain specific. And what's not acquired stably at all is all of these reasoning tasks. So this is interesting. So it seems like now there are two sets of results. And at a first pass, you might think that they're maybe contradictory. So these models are superhuman at certain kinds of tasks, but then there are these other results that show that maybe no, there are other tasks that they do really poorly on, even things that are very simple to just heuristically think about if you know anything about language. So then the question is like, how do we make sense of these results? So my argument here, and what I'm going to say, is that we shouldn't just work on making the models bigger and bigger and being trained on more data. And instead, we really need to take a more nuanced perspective. So it's not that language models are the way to go or they're not the way to go. It's more that we have to think about how the use of these pre-trained and fine-tuned language models interacts with the evaluations that we want to pair them with and what we care about wanting to do. And so that's going to be the main argument. So that we need to think about this, and we need to have a way to structure the different types of evaluations and data sets so that we can then figure out where we need to build in our own knowledge about how the world works in a way such that the models will work better. And so my perspective is like the perspective of NLP technologies. So we have to think about, do we care about the words or the semantics? And then for a particular NLP task, what type of capability is needed? So just to call back to the results, the neuroscience results by Fedorenko, Shrimp and Fedorenko, what they would say if you ask them is that there is like a language layer, and then there's like a thought layer. So the language layer would be like predicting words and contexts and so forth, and predicting reading times. And all of these results from that perspective are actually not super surprising now that if you think about it, because like we've known for a long time that like reading time and surprisal, some notions of surprisal do correlate strongly with like language model probabilities, and all of their behaviors and so forth are about reading. And so they make this distinction between that kind of linguistic, what they call a linguistic layer versus like some kind of thought layer, which is not supposed to be handled by language models in the first place. And that's great. And maybe from a neuroscience perspective, it makes sense to divide things in this way between language and thought. But then from the perspective of NLP people, we are interested in solving these problems and applied problems where there are task internal logics we have to care about. And so then that's why it becomes interesting to think about how should we decompose a task into like the various logics versus, and the various ways you could solve that task using like task-specific cues and heuristics, and whether it's okay to do that. All right. So then I'm going to focus in particular on entities and the dichotomy between words, which are these linguistic level things that you can define. In fact, even there, the definition is not like entirely clear, but let's say like words in terms of like how BERT or some other language model chooses to define them, maybe even subword tokens. Okay, so something at the linguistic layer where you can then apply a pre-training, a transformer style architecture to do pre-training and fine tuning, versus what we often care about a lot in an NLP task, which is insights about the entities themselves, where entities can refer to like a person in the world, or may refer to like some kind of abstract idea or concept. We can also then eventually talk about like events and relations and so forth. It's just that there things become even more complex. So okay, maybe let's focus on entities for now. And so then I'll talk about how we can organize the different methods that we have available to us in order to handle this mismatch that exists between words on the one hand and entities on the other hand that we might care about. And so I'll organize these tasks in terms of the levels of explicit entity awareness that seems to be required to solve them. And so then I'll also talk about the models within these classes that seem to perform well at those related tasks. So then you can talk about models that have no awareness at all, and it only works at the level of the words, much as you see for the currently predominant paradigm. And then we can start talking about maybe there are models where entities can be distinct from the words and phrases. And at least there's this idea that there's an explicit distinction between the words you see versus entities, and it's not just all encoded implicitly in the hidden layers of a transformer. And finally, maybe then an even further direction would be to have these entities have rich internal structure so that you can do even more precise types of reasoning with them. And so then the rest of this talk will be about examining the successes and limitations of models that work at these levels and the kinds of tasks and evaluations that we need to pair them with in order to really evaluate the performance there, to see whether these types of models are getting at what you want. And of course, it's going to be heavily biased towards the problems that I've worked on related to computational discourse and natural language generation. All right, so if there are any questions, please feel free to raise your hand or to just type in the chat, and then I'll be happy to take them throughout the talk. All right, so the first level of entity awareness that we can talk about is the case where the models have no awareness at all. So maybe the awareness is implicit. And so we directly work at the level of words or word pieces. And maybe we can even add like some syntactic annotations like part of speech tagging or parsing and so forth. But there's no explicit distinction about something that's a part of a word or a phrase versus something that is like an entity in a semantic sense. And most current work in NLP, I would say, it falls within this paradigm. And this paradigm has actually been extremely successful, as you saw, at least in terms of the evaluations and tasks that we've used them for. And it seems that if you summarize the types of tasks that this works well for, this would involve tasks involving extracting linguistic structure, like extracting part of speech tags or doing some kind of parsing or discourse parsing, text classification, information retrieval, and so forth. On the more computational discourse side, then this also includes tasks like coherence modeling, like next sentence prediction tasks and document ordering tasks, and also some generation tasks, at least the generation tasks where the amount of semantic inference and semantic reformulation that you need to perform well is limited. So for example, in terms of work that I've done with collaborators, we've worked a bit on coherence modeling, where it seems that explicit entity representations are not really necessary to solve the traditional tasks that have been associated with coherence modeling. So in coherence modeling, one very popular setup of this is to have a bunch of sentences, and you have to reconstruct the original ordering of the sentences as they were found in the wild. And that's one approximation of coherence models. And the idea is that if you can reconstruct how the sentences were originally ordered, you understood something about the original logical way in which a passage has been formulated. And we were able to do this really, really well, just using a model with no explicit entity awareness. So we did this work just before BERT became super popular. The way we did it was we had, again, RNN encoder with some pre-trained word embeddings, and we fed it through multiple layers of a neural network to do a prediction of to do a next sentence prediction task. And this worked really, really well. And in BERT itself, they also did a next sentence prediction task. And in some versions of BERT they included, and some others they don't. But anyway, so the idea is that you can do next sentence prediction really well. You can also do this in a slightly less contrived setting. So you can do things like predicting the readability scores of passages. You can also use it to predict the complexity of passages. Other people have tried that. And then you can do some other kinds of text classification tasks related to coherence modeling. And so yeah, for this style of task, it seems that you don't really need explicit entities. It seems that there are enough regularities in terms of just how a text is formulated that you can get very high levels of performance. Another kind of task where you can get very high levels of performance without needing explicit entity representations is actually summarization, at least for certain kinds of summarization, for certain ways in which you evaluate summarization systems. For example, in one work, we showed that you can do extractive summarization of scientific articles, and you can do it really well just by relying on a few heuristics along with modern representation learning techniques. So this is work by one of my PhD students, Yue, who I think gave a talk here at Waterloo a few weeks ago. And what she did was that she came up with this extractive summarization system that relies on the stereotypical discourse structure of how a scientific article is written in order to help models figure out where important information tends to occur within a scientific article. And by doing this, we can have the system that picks out these sentences that are very similar, or are much more similar to the way that the abstract of the article is written, which we take to be a proxy of the summary of the article. And so this shows that there's some regularities in terms of how scientific articles are written in a particular, say, venue. And you can exploit that to come up with these systems with just a few hand-coded heuristics in terms of modifying the importance scores that you derive from a representation learning technique. And so this works really well. If we consider this style of work to be unsupervised, then we can actually get our model, which we call HippoRank, to perform just as well as supervised models that are trained on hundreds of thousands of these article summary pairs. And so that's great. And this again shows that if you're able to exploit these types of problem-specific and domain-specific heuristics and cues, discourse cues, for example, then you can do really well without needing to build a lot of semantics into your system. And a third kind of evaluation of a third kind of task that we've worked on where you don't really need any deep semantics is a sentence rewriting task that we've worked on, which is where, so now it's no longer purely extractive in that you're no longer just extracting sentences from your source text and putting them into your summary. Instead, you also have to think about rewriting, but a particular form of rewriting. So for us, it was about articles. So articles like a V or A or nothing. So determiners in linguistic speak. So another of my students, Ajad, worked on this problem, and he showed that you can have a separate post-editing step that can rewrite some original extractive summary that from a current extractive summarization system and redo all of these predictions about the articles. And you can do it in such a way that human judges of those same summaries would then think that the new summary is more fluent and it reads better, it's more coherent. So these results are results of 3 annotators and their preferences. So they, by far, they prefer the version of the summary that has been modified by our post-editing system compared to the original, which is the original system produced by the extractive summary writer, which is the second bar here. And again, this is great. This has like practical uses. You can improve the quality of your natural NLG system output by doing this, and you don't need to think deeply about semantics. But again, if we think about how these evaluations work, it's about looking at, say, the overall level of quality. It's about looking at how fluent these outputs are, and asking humans to look at their preferences that way. And so for these styles of evaluations, it seems like then there do exist perhaps shortcuts or other things in the data set that we can exploit and use and get high levels of performance. Yeah, so here in these types of models, I would argue entities and events are implicit. And that's great. And then these fine-tuning tasks where we predict the next word in reference to, with respect to the reference output using cross-entropy, which is a very common style of training these types of models, can help us do this, solve this type of task, or even just supervised learning in some cases, for cases where it's some like a text classification task. But then we can start to talk about some of the limitations. So if that's all you care about, then great. So no need to think about like explicit semantics. But often we care about other issues, even in text generation and language generation. So for example, another really important criterion for NLG outputs is that the outputs are factually correct. And so one thing that people have noticed in the outputs of NLG systems is that actually often they can contain hallucination, so things that are actually not supported. So this is in particular important in summarization, because in summarization we have a source text, and we have to pick out what is the important information and omit the rest. And then within the information that we do select, we have to make sure that we only regenerate the outputs in a way that is consistent with what was contained in the source material. The problem is that in the way that these level 1 systems with no explicit semantics works, is that the training criteria and all of that, they don't necessarily respect this constraint, which is essentially a semantic constraint, that the outputs must be semantically consistent with the inputs. If you think about the training process of like doing some kind of a cross-entropy based word prediction task, that's at the word level, which say the linguistic layer, and not at the thought layer or the semantics level. And so then it seems that then it would be pretty intuitive and it would make sense that these models achieve high levels of performance according to standard evaluation measures, which also work at the word level. So for example, if you have worked in NLG, you might be aware of like the blue measure for machine translation, or the rouge measure, which is a similar measure for automatic summarization, which compares the word overlap between the output text that has been produced by the system versus a reference standard of the output's text. And so you can achieve very high levels of performance there because the output has very high word and n-gram overlap with the reference output. You can also even get very good human preference judgments. Again, because the human judges, if you don't carefully tell them how to do the evaluation, they might be biased towards thinking about what reads very fluently, what seems like it's a very good machine translation output or a very good summary. But now if you talk about this other issue, which is essentially a semantic issue of like whether or not the output contains a hallucination, then suddenly the story changes quite a bit. So abstractive summarizers, there have been studies that show that they do hallucinate. And when this causes problems, this causes a major problem. This is a major problem. Here's one example. There's an original article talking about the victim of a terrorist attack, along with the victim's wife. And so in the original output produced by an abstractive summarizer, you can see that there's a major problem because it identifies the wrong person as the victim. It identifies the wife rather than the husband. And so what we would like is to be able to correct this and to be the correct person who actually was the victim. And this problem is more prevalent than you might think. It turns out that in one study, about 30% of generated summaries actually contain this type of entity level factual error. And there's been a number of evaluations and data sets that have worked on this issue in the recent literature, including some work that we've done. And so we've worked in the space as well of evaluating and correcting model outputs by having a separate step that really focuses on whether you can trust the outputs of these systems. And so this is a problem, and it shows that some of the issues with like not thinking explicitly about semantics, that perhaps the correctness then becomes an issue. So then the overall point here is, so there's this particular line of work, which is interesting, but I'm not going to go further. The overall point that I'm trying to make is that people are really good at finding patterns, and we're very naturally tuned towards that. And you have to be very careful when setting up your evaluation of NLP systems or even just machine learning systems outputs in general, because it's really easy to fall prey to this and think that your system is doing something really fantastic when actually the performance might fall apart very quickly upon any kind of like probing. And so envision this, you can have a parallel phenomenon called, I can't say this word, pareidolia, okay, where you have inanimate objects, and because people are so keen and so geared towards finding patterns, and in particular faces, because I guess that's really important from like an evolutionary standpoint, that we can create these faces out of like arrangements of objects that happen to perhaps look like faces. There are certain features that make them look like faces. And what I'm saying is that for NLP systems, there's a parallel thing going on, and it's important to be aware of this potential bias and not delude ourselves into thinking we're doing better than we are. So fluent generation, in other words, is not enough because it really exploits people's tendency to look for patterns and intent. And so then you can think of this as some kind of textual pareidolia. Okay, so another recent study that I think is really great was that it's been shown in the last year that you can get human judges and ask them to distinguish between automatically generated passages versus human written passages. So the automatic passages were done by GPT-3. And you can show that if you don't set up the experiments carefully, and you just tell them which one is human authored, which one is machine generated, people can't really distinguish between the two well. Okay, so you can read these stories, and the human authored one looks really good because it's human written. And the machine generated one also looks really decent because in terms of the form of it, it's very plausible. If you read the machine authored one a little bit more carefully, then you can start to see that there's something weird. He sat there for a long time not knowing what he was doing there. He thought, but he didn't know what to think. And like each sentence is locally like coherent, right? But like it seems like it's not moving the story forward very well. And so even there, you can see that maybe there's some issue with like diversity of like what's generated or like the higher level progression of the story. But still at a high level, it looks very fluent. And so we might be like tricked into thinking that is actually human-like. And so because of this, well, I guess the reaction to this is either, okay, let's just throw even more data with a bigger model at it. And I think it seems to me that this way, even if it works, the progress will be like you need an order of magnitude more data and more parameters and more training in order to get a slightly better generalization performance. Or the way that I would perhaps advocate that we should spend more time thinking about is to think about maybe going back to some ideas from semantics and linguistics about explicitly modeling, having an explicit layer that's separate from the linguistic level, which is about the semantics of the situation. And so that's what the other two levels are really there for, that I'm going to argue for, that we should work on. And this might give us a way to really get better performance at the types of issues involving semantics that we care about. And so in terms of the remaining two layers, the second layer would be a level of explicit entity awareness, where entities exist and are distinct from words and phrases. And so then this might mean that there needs to be some extra processing that goes on to be able to recognize what actually are entities. And this might involve, say, coreference resolution or entity linking. But we can see, like, what is this actually bias and why is this useful? So just having entity representations alone doesn't automatically solve some of the issues I talked about earlier, but here are some of the potential advantages. So one is that there's persistence. Okay, so if you have just words and phrases, you have to think about like the persistence of these words and phrases over a discourse and how multiple occurrences of a word relate to each other and whether they're referring to the same real world entity. But if you have an explicit entity and you're able to correctly link that to the words, you've like factor that out, and then that would be a big advantage. So you can talk about how an entity evolves over time, or even how an entity occurs in different documents altogether in different discourses, but it's like the same real world entity. And so you can talk about like Joe Biden and what Joe Biden has been up to, and you can store information about Joe Biden separately in his Wikipedia article versus in each of the contexts in which you see Joe Biden, and that would be really useful. And so this kind of persistence will let us do better knowledge integration across multiple knowledge sources. I also think that having these types of explicit entity representations allow us to do a better job of abstraction, which is more of like a thing that we might care about for summarization. So it lets us perhaps do a better job of reasoning and to spot trends and so forth. And to also, if you have like abstractions of like what the words refer to, you can then you can recognize that there might be conflicts between how different people talk about the same thing and like different kinds of information, and then start to think about how you might want to handle information conflicts about the same entity. So as an example of this style of work, you can have an automatic summarization system that does this. Here's one recent work that I like from Shashi Narayan, where he has an explicit entity level representation, which still works very well with all of the advances in like pre-trained language models that are fine-tuned. So in his work, he has an explicit level where there is a target with an entity chain, so that he has a separate step to generate. Here's a chain. Okay, let's, yeah, sorry about that. Let's hope my phone holds up. All right, so yeah, so this was, I was talking about the summarization system, which I think is cool because it demonstrates how you can have an explicit level of entity representation in a very simple way. And they can show improvements in terms of controllability and reducing hallucination and so forth. And as I said, I also think that having explicit entities will allow us to do more. It'll allow us to do more kinds of abstraction tasks that involve more reasoning. And so let me show you one of the evaluations that we've worked on and proposed in the group recently, which is about this issue of abstraction. So for us then, abstraction means more than just writing and including words that are not in the original source document. Abstraction really means aggregating information by finding out what's similar between different entities and different things that are referred to in the source text, and then trying to express them together in the summary text. And so then we're thinking about this semantically in terms of a change in the level of specificity between the source text and the summary. Let me give an example. So here's a movie summary for the movie The Dark Knight. So it says something like, it succeeds not just as an entertaining comic book film. And then if you look at the actual source material from which you can conclude this, it says it's quite, the rephrasing is quite complex. It says like the Dark Knight right now is that the highest compliment that this reviewer can give to it is that there are long stretches where the reviewer doesn't even realize it's a superhero movie. Or here, there's one single noun phrase, crime saga. And to figure out that this is a crime saga, you have to look at the review text and see that it talks about lots of particular instances of crimes, like corruption, betrayal, violence, and tragedy. And to make it a saga, it needs to be some kind of like long involved thing. And so here it's expressed as extremely large. And so this is the kind of aggregation that I'm interested in. So we have especially like crime being like corruption and betrayal and violence and tragedy. Right? So these are particular instances of potentially crime, and it's summarized into a single noun phrase. And so we proposed a data set where you can at least start to work on this problem. So this is not something that people have like thought much about in the natural language generation literature. And so as a first step, then we need to have some data set, so at least we can do evaluation. And so that's what we did. We proposed this data set called TESSA with an associated task, which is to generate a single and non-enumerating noun phrase that summarizes and covers multiple entities on the input side. And this is done in context. So you can't just like look up the taxonomic relation and call it a day. For example, one instance in our data set involves François Bayrou, Nicolas Sarkozy, and Ségolène Royal. And so then in the data set, then these can be aggregated as the French politicians, or in the context that we presented, it might be the French presidential candidates, or just the politicians. And so we constructed this data set by drawing from the New York Times and getting crowdsourced annotations from humans. And this is the interface that we showed. So it shows the multiple entities here in the color, like Royal, Sarkozy, and Bayrou. And then it gives some background information, because in this task, we found that background information about these entities is really important. And then in this context, we ask people to like replace those noun phrases with a single noun phrase that can describe all of them, and that's appropriate in this context. And so this is the beginnings of the effort. This is by no means a solved task. So beyond this, you also have to integrate these noun phrases into an actual output summary or sentence. But at least now we can start to evaluate how well do systems actually perform at being able to recognize that entities share a common property. And then you can use that common property to denote them as a group, so that you can then start talking about what's common between other common properties or relations or events that happen for this entire group. And so we ran some preliminary experiments by like doing some fine tuning. So on our data set, and you can have like some kind of generative version of this or discriminative version of this, and you can get some good performance at ranking the different possible aggregations. I don't think these results are particularly the most important for the purposes of this talk, but it's just to show that you can fine tune and get this improved performance. And then you can look at the outputs generated by our system, which is like a preliminary thing you can do with our data set. So one really interesting thing you can see is already that, so our model is a very simple model that just takes our annotations and fine tunes on it. And so you can see that like in the generative version, it exhibits some of the same issues that I talked about earlier with models that don't have explicit entity awareness, which is that it generates that these three entities, Francois, Nicolas, and Ségolène, they can be summarized by like New York mafiosos, okay, or like people involved in the scandal anyway. So the generative version does have the same kinds of hallucination problems as we saw earlier. So yeah, I'm getting near to the end of my time. So I just want to quickly then talk about like what's the third level. So we can have models that have no entity awareness, have some preliminary entity awareness, either in terms of the model itself, or at least in terms of like the output task that we want to evaluate with. And beyond that, what else can we do with these types of representations that is more than just saying that there is something that's separate from the linguistic layer? And I think there's more to do there. This is perhaps even a little bit more medium term or further ahead into the distance, but I think here is another area where maybe some insights from linguistics or insights we might have about like from psychology even could be useful in how we design our machine learning methods for NLP. So in particular, in terms of entities with rich internal representations and structure, it's really important to realize that for some kinds of entities have internal mental states, and we might want to model them explicitly. For example, there have been some frameworks where you can talk about mental states in terms of the beliefs, desires, and intentions of entities. So entities can have beliefs that might conflict with other entities' beliefs, or might conflict with the real world if we have some way to like know what is reality. They might have desires that if we model, we can better predict what they might do in the future. And similarly, intentions, which are like how they turn those desires into what they will try to do. And so there have been some individual papers that have looked at individual parts of this. Like there have been some cool work on like looking at negotiations and like board game setups with NLP agents, or like setups with like board games where like you have to like, it was like a diplomacy board game where like people might like deceive you and like turn on you and so forth. And so more generally, one way in which we can have rich internal representations of entities is to have entities that have a theory of mind, or systems that have a theory of mind. And this would be important, for example, for dialogue systems or game-playing agents, or even just to have more robust versions of common NLP applications. And again, I'm running out of time, so I'll quickly go through this task setup, and then we can wrap up. So for example, here's one concrete example of how work from psychology can help us, inform us in terms of how we design these types of models. So in psychology, there's something called a Sally-Ann task, which involves a test originally designed for children, which involves like conflicts in terms of the state of the world versus the state of belief of an entity in the world. In the Sally-Ann task, how it works is that you have two people. The child is presented with two people, Sally and Anne. And they also see two locations, like a basket and a box, and they see like a red ball in the basket, for example. So what happens is that Sally leaves the room, and the child sees this. And then the child sees that Anne moves the red ball from the basket to the box. And then Sally comes back in, and the ball is in the box. And then the child is asked, where would Sally look for the ball? And the idea is that children after a certain age, and also adults, would figure out that Sally would look for the ball in the basket rather than the box, because Sally would not have observed the change in the state of the real world in terms of where the ball is. And so then that's a case where this entity in this world, like Sally, has a different belief that is different from the state of the actual world. And we'd like to have NLP systems be able to model this as well. So they can model knowledge states of different users and help them answer questions and help them remind them of things and so on and so forth. And so our work, we followed some recent papers that have converted the Sally Ann task from something designed for children towards something that's in textual form that has been designed for NLP systems. And the short version of this is that by incorporating priors about the entities and how they work and the fact that they can have different mental states, we can design variations of these models that are much better at solving these tasks. And in particular, it's much better at solving the tasks where there's a conflict between the state of the world versus the state of knowledge of an entity. We get like a big performance improvement on that style of question, which are this set of question called first order false belief tests. And we do this by building assumptions about how the world works into the model through either heuristic means or by setting up a multitask learning environments. So we build assumptions like the fact that entities can only observe locally changes in the state of the world based on where they are, as described in text. We have to build assumptions about like where entities will assume things are based on like the recent state of the world, and that entities will assume that entities work in the same way as them, that the other entities also behave according to local perception and recency. And we can design heuristics that implement these styles of these assumptions and show the performance improvement. So I'm going to skip how the model works. It's a variation of a memory augmented network. And then we gave it like some cool name, like a time travel or whatever, because the way our model works is that it looks at different points in the text. So it's a kind of textual time travel. And then we can show improved performance, especially on these first order false belief tasks. So in the original model, that's just a memory network. It gets like 68, and we can improve that up to like close to perfect. All right. So yeah, just to wrap up overall, again, the main point of my talk is that there's a lot more going on in NLP that's very interesting, and that we don't have to resign ourselves to only looking at how to train bigger and bigger transformer networks. And I think a lot of the successes are real successes, but you have to really be careful and take a nuanced view about the successes, because a lot of them, the news headlines you see and so forth, they talk about the average case scenario where they have particular kinds of performance metrics where you don't have to think carefully about the semantics, about like correctness or fairness or bias and so forth. And so depending on what you actually care about, if that's all you need for your particular task, then that's great. Then the current models will serve you well if you have a lot of representative data. But it's really important to like also think about like what happens if you perturb the setup a little bit, or what happens if you're interested in other kinds of evaluations or other kinds of tasks that require more reasoning or semantic processing. And I think there's still a lot of room and a lot of work to do in figuring out what's the best way to do this. So it's not clear at all that just increasing the size of what we work with will automatically solve everything, especially not in a way that's very practical, that like you can tune on a new task that you care about in a new setting. And yeah, so there's no need to pick any of these levels of representation, but I would argue that if we spend more time working towards like the levels of representation where there's more explicit semantics with like higher levels of entity awareness, then that will improve the variety of tasks that we can solve. And it can also help us improve the confidence we have that our models are actually generating something that is correct and controllable. And as part of this, I also then say that this also lets us leverage like all of these existing sources of information in a much better way. So rather than just thinking of everything as text and throwing them all in, we can do a better job of leveraging structured resources. And if we do entity linking, then we already have a lot of knowledge about existing entities that are well known enough or popular enough to have their own Wikipedia article, for example. And so there are lots of interesting research questions and directions here about like what are the model architecture changes and what's the level of like assumption that we need. Like, is it just the idea that there are entities, or do we need to build something more that they have like internal mental states and representations? And so that's all open. And I really want to encourage more people to think about these types of things, work on these types of things. All right, so yeah, sorry the ending was a bit rushed, but I'll conclude there. I just want to thank my amazing students who are doing all the work, and also my wonderful collaborators at MSR Montreal and Google Research and at other places. And this work is funded by NSERC and MSR and Samsung and CFAR. And I'm happy to take any questions.
All right, well, thank you very much. Great talk. Okay, yeah, do we have any questions for Jackie? Okay,
so yeah, so I see Saman has a question. Yeah, are transformers still the best models for the different tasks that I described? Yeah, so I think, again, you have to think about like exactly which task and which evaluation measure. So for a lot of them, transformer-based methods are the best, right? So almost all of the ones that I've described, according to the standard evaluations of like rouge or blue, transformer-based models are the best. The only exception I can think of is in authorship attribution. So that's one evaluation where I've worked on, where like simpler models that look at like a simple classifiers based on like character level features and so forth, it is competitive and possibly better than transformers. But for most current NLP tasks in terms of how they're evaluated, transformers are the best. And then for all of these other evaluations of robustness and perturbations tests and so forth, then there's an active research area going on how to like fix the transformer models so that they can actually also do well in these settings.
Well, so Jackie, I mean, here you just gave us a talk about how entities are important. And I was expecting you to answer this question by essentially saying, no, transformers are not the ultimate thing. We need to incorporate something or do something about entities. So you did not go into a lot of details about how entities are represented, but then would you still say transformers are the way to go? And then how do they capture entities?
Yeah, that's a great question. So I do think that transformers are the way to go, at least for getting an initial representation of the linguistic layer, the words in the context. But we can add on top of that, we can have further representations. For example, either as part of the same training or like with additional layers and so forth, or maybe just having an explicit separate step to do coreference resolution, where we can then have entities and then link that knowledge into the built up representations we have from the transformers. So yeah, I think that's the next interesting thing to think about and work on.
Okay, but then,
yeah.
I mean, in the last part of your talk where you talked about, I guess there's some level 3 rich representation for entities. So how exactly are entities represented there?
Yeah, so I didn't have, oops, I ran out of time, so I skipped that part. But so for us, how we did it was that we tried different things. So we tried to set up a memory network where you have different memory slots. And then we were hoping that the memory slots, that the information the model will choose to write there will correspond to an entity that we can analyze and recognize from the text. It turns out that this doesn't happen automatically. And maybe like that makes sense because like transformers, you can think about draw parallels between like transformers and like memory slots and memory networks, and maybe so this is maybe just more capacity for the model that the model works on. So I think we can do a better job of like trying to enforce that constraint and see whether interesting things happen there. And we're currently working on like evaluations and models that require this. So for our purposes, how this worked was that for one version of the model, we forced the model to know about what entities are, that they had to know that Sally is an entity and Anne is an entity, and then they can figure out how to solve the problem by, in this version, we directly tell it, you have to go to the last time step where both entities are mentioned in the context. And this will help us solve like this first order false belief questions. And then we had another version of this where the entity representation is kind of built into the task setup. where at each point in time, we get the model to predict and answer what is the location of each of the entities. And so then there's no, here the representation is kind of in terms of the prediction of the model for where the entity is. And so that's one property of where the entity is. And then we can use that with some heuristics to answer the question. So right now it's very much built into these heuristics and into the task setup. And it's not so much one thing in the representation that you can point to in the model itself. And I think it would be really interesting to get maybe a little bit more of a principled way to like build up these entity representations. And it's something that we're working on right now.
Okay. So there is another question in the chat. Are you able to see it?
Yes. Okay. So Michael asks, have there been attempts to integrate huge knowledge bases like Wikipedia or Google into transformers models to get better NLU? Yeah, I think there are some attempts at doing this. So there's some attempts at, for example, doing retrieval. So you can do retrieval to extract relevant passages or relevant entities. And then what those types of models do is that you can then feed them into like some intermediate level of the overall model and then do further processing of that. So yeah, I think that would be really interesting. It'd be good to test those types of models some more. The work that I've seen in this space has been like, some of it has been pre-BERT. So yeah, I'm sure somebody has been doing this like recently as well. Recently, the trend has more been like, let's do a retrieval and like pass it into the context and like change like the prompted context in order to like do some better generation. And that could be a good baseline to work on as well.
Mm-hmm. And I actually, along the same lines, so a lot of people are complaining that BERT and all these other language models, often they don't have correct facts, and perhaps they shouldn't be storing whatever facts happen to be from their training data. And perhaps it would be nice to have a separation of maybe the language part versus the facts. So what's happening in terms of perhaps maybe designing the next generation of language models that would do this type of separation if it is a good idea?
Yeah, so I think it is a good idea. And even in terms of the facts, there are multiple layers, right? There are general facts about the world, like Joe Biden is the president of the US, and that can even change and update. And then there are facts and knowledge and rules and things that are specific to that particular context that the model looks at, which don't necessarily transfer between different instances. So yeah, I agree with that. I think, yeah, I think it'd be great to separate all of them and have different representations. For example, you can imagine doing some kind of graph neural network on like the general facts that it's stored in a structured knowledge base. Yeah, I think the challenge is that you need to like integrate all of this, and you have to find a way to convince people it's a good idea, because for any particular evaluation, there's probably one of these ways, which is like the way that best matches your evaluated output. And then you should just use that. But then it becomes like kind of a evaluation specific choice. So I think the challenge is to set up the right evaluation suite so that you can convince people it's like generally the right thing to do. So yeah, perhaps that's what we should be working on. Like, yeah, so some kind of knowledge integration tests and a benchmark where where separating all of these different levels is important.
Yeah, because at least as academics, we don't have the same access to resources as perhaps large companies. And then so for us to experiment with these super large language models is often prohibitive, right? So I guess, okay, even if we can't necessarily have like the best score on a task, if on the other hand, we can obtain something scalable, there's value, right? And then would it make sense if we do this type of separation to have perhaps a smaller language model that is more reasonable, at least for us in academics, we could work with. And then, okay, you have the large knowledge base on the side, and that can be stored presumably in excess as needed and using whatever techniques we wish, right? So yeah, so would that be maybe a way to perhaps justify this line of research?
I think that could be a way to justify this line of research. So I think a lot of the stuff I do is like in terms of evaluations on a smaller scale that I think can scale up. So then we should test models that way. I think there's some criticism that people could have, which is that there might be some generalization effects. Like the scaling loss, people like to say that there's some generalization effects where there's a phase shift, and then like if you get enough data and like large enough models, then suddenly things will generalize systematically. I guess so far I'm not like, they've shown this for a few artificial settings, but I'm not super convinced it'll happen all the time. So I still think it makes sense to like come up with these scalable evaluations and scalable models.
Okay.
And test according to them.
Okay, cool. Maybe one more question, just going back to what you were describing earlier with, I guess, some type of memory network. And you said that it was hard to obtain, I guess, a representation and that satisfied, I guess, perhaps what you were looking for. And then here is the issue, perhaps the fact that these things have to be, I guess, unsupervised or self-supervised, and therefore we lack interpretability to really say that what's being stored in the memory is really like this entity versus that entity versus something else, and so on.
Yeah, I think that's one of the problems, and that's why we switched towards. So the heuristic method is really hard coded, and the way we try to relax that is then to then solve these auxiliary questions, because you can imagine that it's relatively easier to justify like getting a model to predict what's the location of all of the relevant entities. Like you can imagine like an AI agent and system, or like just living organisms in general care about like the existence of entities and where they are and trying to keep track of that. So that's maybe easy, that's easier to justify. And so then you can try to solve these auxiliary tasks. So we haven't done the analysis of doing of like whether this type of auxiliary task would lead to like memory storage slots that are more interpretable or that correspond better to entities in the world. But yeah, I think that's that's the motivation for like these auxiliary tasks, is to think about auxiliary tasks that might be useful for an agent generally, and then hope that it leads to representations that are also more interpretable.
Okay, and so here those auxiliary tasks, I guess, yeah, they can help at least at training time to make sure that you've got the right information into your memory, and presumably at test time they can serve as, I guess, as probes to, I guess, presumably just extract information. So even if in the memory we just see numbers, we don't know what they really store, the probe can essentially extract what's relevant there. And then it's a matter of training these additional probes, right?
Yeah.
Okay. Nice. So then what do you see going forward in terms of perhaps better representation? I mean, I guess, yeah, we've got these memory networks. We also have, I guess, with transformers, just these embeddings and so on. So do you see anything that is promising, that is different from what we're familiar with?
Yeah, so for me, I think the key thing is to separate out the different kinds of knowledge. So general knowledge, instance-specific knowledge, and linguistic knowledge, and have separate representations for that. I'm still just at the beginning of thinking about what's like the right technical approach to like do all of these and integrate them. So I don't think I have a good answer for you there. But I do think that the key like theoretical insight is to keep those things separate, because that draws on a lot from both like linguistics and like the early AI, classical AI thinking and research. And for me, the main current technical thing I think about is like, what are the evaluations we can design so that we can begin to like experiment and find the right technical architectural approach to solve those problems. So that's why I focus so much on data sets and evaluations, because I think that otherwise there's no hope of like telling what's like the right way to go with the existing evaluations. Yeah, so that's my, I guess, philosophy.
Great. Okay. Does anybody have any other question for Jackie? Okay, well, if not, then let's thank Jackie again. So great talk, and very interesting ideas. So thank you, and I wish everyone a good afternoon.
Yeah, thank you so much.